In this video we will look at inverse functions. We have first a function, and then we know we have a one-to-one function where we can test whether it's a one-to-one function, and from there onwards I can find the inverse of any one-to-one function. So this page is again just a summary of the theory of one-to-one functions. On this page I give steps how to get the inverse of a one-to-one functions algebraically. So number one, you swap the x and the y. Then you solve for y, and then you replace y with f minus 1x. So you again have f minus 1x is equal to x something, whatever the function is. Graphically, you will find the x and y-intercept of the initial function, and then we draw that graph, and then we draw the line y equal to x, because the inverse function will be reflection about the line y equal to x of that function. So then we can also swap the x-intercepts and the y-intercepts for the inverse function, then we draw that as a reflection in the line y equal to x. It sounds more difficult than it is. So let us do some examples. Here I have a straight line y equal to 3x minus 2. And we know with every straight line is one-to-one. I know what the domain is. I can every real number put into this 3 times x and subtract 2 and get a real number as an answer. So the domain in the range both will be R. So if I swap x and y, here we have x and my y and my x. And now we swap the y and the x, so I will have x is equal to 3 times y minus 2. This is just a swapping. Now I solve for y, so I get 3y minus 2 is equal to x. So I plus 2 both sides. So then I get 3y is equal to x plus 2. So now I have divide by 3, divide by 3. And then I get y is equal to x over 3 plus 2 over 3. This is my new equation for my inverse function. So f minus 1x will be then x over 3 plus 2 over 3. So this inverse of mine, which is now this function, we have the domain and the range the same, but it swaps, but it still stays R. Remember, because we swap the x and the y, we also swap all the other properties of that function. If I do this graphically, then the x-intercept for that straight line, this is where y is equal to 0. So I will get 0 equal to 3x minus 2. So therefore x will be 2 over 3. And y-intercept, if x is equal to 0, I get y equal to 3 times 0 minus 2. So my y is equal to minus 2. This is just my c value. So if I now draw the green graph, or draw that graph in a green line, and I draw the line y equal to x, then I can swap my x and y intercept. So my x-intercept was x equal to 2 over 3. Now my y-intercept, so the x-intercept is a y-intercept of that, but remember it's still an x-intercept, so it's now x equal to minus 2, and the y-intercept is now y equal to 2 over 3. So let's look at the graphs. We can see here at this point we have y equal to minus 2, or the coordinates 0, minus 2. That's the y-intercept. On at this point here is the point minus 2, 0. We can see this y value became the x value there, and this x value became this y value becomes the x value here. So they just swapped. And here we have x equal to 2 over 3, and that becomes y equal to 2 over 3, the two intercepts. if I take any point on the green graph, like for instance there, where x is equal to 2 and y is equal to 4, then the point 4, 2, which is here, must lie on the inverse function. So again, the y swap with the x and the x swap with the y. And then what we also must remember is that wherever we are, we take a line perpendicular on this line y equal to x, then the original function and the inverse function are equidistant from the line y equal to x. And f of x, the green one, is reflected in the line y equal to x. It's as if you take a mirror on that line and then you get the red graph. Let us look at the parabola, and we are going to use the right hand side of the parabola. So the domain is all x greater or equal to 0, and because we have x squared plus 1, we shifted the graph 1 unit up, so the range will start at 1. So everything from 1 up to infinity. So first of all, we swap x and y. So ignore that x. So if you swap x and y, then we get x equal to y squared plus 1. Now we must solve for y. So we get y squared is equal to x minus 1. So to get y on its own, I must draw a square root both sides, and then I get y equal to plus the square root of x minus 1. Remember, here we said that we're going to take the positive x's. So that means now here must be the positive y's. And we can now write the function here, x minus 1. This is my inverse function. And we see that the domain, in this case, if I look at the side, x minus 1 should be greater or equal to 0 before I can calculate that square root. So x is greater or equal to 1. And that corresponds to the range of my original function. I did not go through all the same paraphernalia as I did with the straight line. What I did is I drew the graph of y equal to x squared plus 1, the original function, and I know it goes through y equal to 1 on the y-axis, and then I draw the line y equal to x, and then I draw this function here. If I'm not sure how it looks like, then I can take a few points here on this graph, like for instance there, that point is the point x is equal to 1, y equal to 2. So now the point 2, 1 must be on this graph. If I look at another point, like for instance there, x is equal to 0.6, or let us write it differently. That's about 2/3, and the y is 1 2/5. So then here I must have 1 2/5, because it's 2 small blocks of the 5 blocks, and the height is 3/5. In this case, this should also be 3/5, because it's 1, 2, 3 small blocks. That's the x values. The y values are 1 block plus 2 small blocks. So if I have a few points, then I can draw the graph through that points. And if this green graph is concave up, then the other one will be concave down. And you can also remember that it's sort of the rotated graph of the parabola y equal to x squared plus 1, but then we use the negative side of it to draw that graph.